Hello friends, in the previous lecture we talked about the digital signal processing of analog signals, usually in real time, for the purpose of modifying or enhancing the signal in some way. During the discussion we talked about the basic digital signal processing, and then we learned the process of A to D conversion. In today's lecture we continue further and discuss various types of A to D conversion methods, and then we shall talk about the D to A converters. Analog to digital conversion methods. As you have seen, analog to digital conversion is the process by which an analog quantity is converted to digital form. It is necessary when measured quantities must be in digital form for processing or for display or storage. Some common types of analog to digital converters are now examined. The two important ADC parameters are resolution, which is the number of bits, and throughput, which is the sampling rate an ADC can handle in units of samples per second. Before getting into ADCs, let's look briefly at the element that is common to most types of ADCs and DACs. This element is the operational amplifier, or op-amp for short. An op-amp is a linear amplifier that has two inputs and one output. It has a very high voltage gain and very high input impedance, as well as very low output impedance. When used as an inverting amplifier, the op-amp is configured as shown in part B of the figure. The feedback resistor RF and the input resistor RI control the voltage gain according to the formula in equation, where V out over V in is equal to minus RF over RI, where V out over V in is the closed loop voltage gain and the negative sign indicates inversion. In the inverting amplifier configuration, the inverting input of the op-amp is approximately at ground potential, because feedback and the extremely high open loop gain make the differential voltage between the two inputs extremely small. Since the non-inverting input is grounded, the inverting input is at approximately 0 volt, which is called virtual ground. When the op-amp is used as a comparator, as shown in part C of figure, two voltages are applied to the inputs. When these input voltages differ by a very small amount, the op-amp is driven into one of its two saturated output states, either high or low, depending on which input voltage is greater. Flash analog to digital converter. As shown in this figure, the flash method utilizes comparators that compare reference voltages with the analog input voltage. When the input voltage exceeds the reference voltage for a given comparator, a high is generated. This setup shows a 3-bit converter that uses 7 comparator circuits. A comparator is not needed for the all zeros condition. A 4-bit converter of this type requires 15 comparators. In general, 2 to the power n minus 1 comparators are required for conversion to an n-bit binary code. The number of bits used in an ADC is its resolution. The large number of comparators necessary for a reasonable sized binary number is one of the disadvantages of the flash ADC. Its chief advantage is that it provides a fast conversion time because of a high throughput measured in samples per second. The reference voltage for each comparator is set by the resistive voltage divider circuit. The output of each comparator is connected to an input of the priority encoder. The encoder is enabled by a pulse on the enable input, and a 3-bit code representing the value of the input appears on the encoder's output. The binary code is determined by the highest order input having a high level. The frequency of the enable pulse and the number of bits in the binary code determine the accuracy with which the sequence of binary codes represent the input of the ADC. There should be one enable pulse for each sampled level of the input signal. Dual slope analog to digital converter. A block diagram of a dual slope ADC is shown in figure. A dual slope ADC is common in digital voltmeters and other types of measurement instruments. A ramp generator or an integrator is used to produce the dual slope characteristic. To understand the dual slope conversion, we start by assuming that the counter is reset and the output of the integrator is 0 as shown here. Now assume that a positive input voltage is applied to the input through the switch SW as selected by the control logic. Since the inverting input of A1 is at virtual ground, and assuming that Vin is constant for a period of time, there will be constant current through the input resistor R and therefore through the capacitor C. Capacitor C will charge linearly because the current is constant, and as a result there will be a negative going linear voltage ramp on the output of A1. When the counter reaches a specified count, it will reset and the control logic will switch the negative reference voltage minus V reference to the input of A1 as shown in part B of figure. At this point, the capacitor is charged to a negative voltage proportional to the input analog voltage. Now the capacitor discharges linearly because of the constant current from the minus V reference as shown in part C of figure. This linear discharge produces a positive going ramp on the A1 output starting at minus V and having a constant slope that is independent of the charge voltage. As the capacitor discharges, the counter advances from its reset state. The time it takes the capacitor to discharge to 0 depends on the initial voltage minus V, which is proportional to V in because the discharge rate is constant. When the integrator A1 output voltage reaches 0, the comparator A2 switches to the low state and disables the clock to the counter. The binary count is latched, thus completing one conversion cycle. The binary count is proportional to V in because the time it takes the capacitor to discharge depends only on minus V, and the counter records this interval of time. Sigma delta analog to digital converter. Sigma delta is a widely used method of analog to digital conversion, particularly in telecommunications using audio signals. The method is based on delta modulation, where the difference between two successive samples is quantized. Other ADC methods were based on absolute value of a sample. Delta modulation is a 1-bit quantization method. The output of a delta modulator is a single bit data stream where the relative number of ones and zeros indicate the level or amplitude of the input signal. The number of ones over a given number of clock cycles establishes the signal amplitude during that interval. A maximum number of ones corresponds to the maximum positive input voltage. A number of ones equal to 1/2 the maximum corresponds to an input voltage of 0. No ones corresponds to the maximum negative input voltage. For example, assume that 4096 ones occur during the interval when the input signal is a positive maximum. Since 0 is the midpoint of the dynamic range of the input signal, 2048 ones occur during the interval when the input signal is 0. There are no ones during the interval when the input signal is a negative maximum. For signal levels in between, the number of ones is proportional to the level. The figure here shows the basic block diagram of the conversion process. The analog input signal and the analog signal from the converted quantized bit stream from the DAC in the feedback loop are applied to the summation point. The different signal out of the summing point is integrated, and the 1-bit ADC increases or decreases the number of ones depending on the different signal. This action attempts to keep the quantized signal that is fed back equal to the incoming analog signal. The 1-bit quantizer is essentially a comparator followed by a latch. Digital to analog conversion methods. Digital to analog conversion is an important part of the digital processing system. Once digital data has been processed by a DSP, they are converted back to analog form. In this section, we will examine the theory of operation of two basic types of digital to analog converters and learn about their performance characteristics. Binary weighted input digital to analog converter. One method of digital to analog conversion uses a resistor network with resistance values that represent the binary weights of the input bits of the digital code. Figure shows a 4-bit DAC of this type. Each of the input resistors will either have current or have no current depending on the input voltage level. If the input voltage level is 0, that is binary 0, the current is also 0. If the input voltage is high, that is binary 1, the amount of current depends on the input resistor value and is different from each input resistor. Since there is practically no current into the op-amp inverting input, all of the input currents sum together and go through RF. Since the inverting input is at 0 volt or virtual ground, the drop across R1 is equal to the output voltage. So, V out is equal to IF into RF. The value of the input resistors are chosen to be inversely proportional to the binary weights of the corresponding input bits. The lowest value resistor R corresponds to the highest binary weighted input, that is 2 to the power 3. The other resistors are multiples of R, that is 2R, 4R and 8R, and correspond to the binary weights 2 to the power 2, 2 to the power 1 and 2 to the power 0 respectively. The input currents are also proportional to the binary weights. Thus, the output voltage is proportional to the sum of the binary weights because the sum of the input currents is through RF. Disadvantages of this type of DAC are the number of different resistor values and the fact that the voltage levels must be exactly the same for all inputs. For example, an 8-bit converter requires 8 resistors ranging from some value of R to 128 R in binary weighted steps. This range of resistors requires tolerances of 1 part in 255 to accurately convert the input, making this type of DAC very difficult to mass produce. The R/2R ladder digital to analog converter. Another method of digital to analog conversion is the R/2R ladder as shown in figure for 4 bits. It overcomes one of the problems in the binary weighted input DAC in that it requires only 2 resistor values. Start by assuming that the D3 input is high and the others are low. This condition represents the binary number 1 0 0 0. A circuit analysis will show that this reduces to the equivalent form shown in figure A. Essentially, no current goes through 2R equivalent resistance because the inverting input is at virtual ground. Thus, all of the current through R7 also goes through RF and the output voltage is minus 5 volts. The operational amplifier keeps the inverting input near 0 volts because of the negative feedback. Therefore, all current goes through RF rather than into the inverting input. Figure B shows the equivalent circuit when the D2 input is at plus 5 volts and the others are at ground. This condition represents 0 1 0 0. If we Thévenize, that is, according to Thevenin's theorem, the circuit is reduced to an equivalent voltage source in series with an equivalent resistance. So, looking from R8, we get 2.5 volt in series with R as shown. This results in a current through RF of I equal to 2.5 volt divided by 2R, which gives an output voltage of minus 2.5 volt. Keep in mind that there is no current into the op amp inverting input and that there is no current through the equivalent resistance to ground because it has 0 volt across it due to the virtual ground. Figure C shows the equivalent circuit when the D1 input is at plus 5 volt and the others are at ground. This condition represents 0 0 1 0. Again Thevenizing, looking from R8, you get 1.25 volt in series with R as shown. This results in a current through RF of I equal to 1.25 volt divided by 2R, which gives an output voltage of minus 1.25 volt. Figure D shows the equivalent circuit representing the case where D0 is at plus 5 volt and the other inputs are at ground as shown. This condition represents 0 0 0 1. Thevenizing from R8 gives an equivalent of 0.625 volt in series with R as shown. The resulting current through RF is I equal to 0.625 volt divided by 2R, which gives an output voltage of 0.625 volt. Notice that each successively lowered weighted input produces an output voltage that is halved, so that the output voltage is proportional to the binary weight of the input bits. performance characteristics of digital to analog converters. The performance characteristics of a DAC include resolution, accuracy, linearity, monotonicity, and setting time, and each of which is discussed here. Resolution. The resolution of a DAC is the reciprocal of the number of discrete steps in the output. This, of course, is dependent on the number of input bits. For example, a 4-bit DAC has a resolution of 1 part in 2 to the power 4 minus 1, that is 1 part in 15, expressed as percentage. This is 1 divided by 15 into 100, and it comes out to be 6.67%. The total number of discrete steps equals 2 to the power n minus 1, where n is the number of bits. Resolution can also be expressed as the number of bits that are converted. Linearity. A linear error is a deviation from the ideal straight line output of a DAC. A special case is an offset error, which is the amount of output voltage when the input bits are all zeros. Monotonicity. A DAC is monotonic if it does not take any reverse steps when it is sequenced over its entire range of input bits. Accuracy. Accuracy is derived from a comparison of the actual output of a DAC with the expected output. It is expressed as a percentage of a full scale or maximum output voltage. For example, if a converter has a full scale output of 10 volt and the accuracy is plus minus 0.1%, then the maximum error for any output voltage is 10 divided by 0.001 and is equal to 10 millivolt. Ideally, the accuracy should be no worse than plus minus half of the least significant bit. For an 8-bit converter, the least significant bit is 0.39% of full scale. The accuracy should be approximately plus minus 0.2%. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learned that sampling is the process of converting an analog signal into a series of pulses, each representing the amplitude of the analog signal. A sampled value is held to allow time to convert the value to a binary code. The minimum sampling frequency is 40 kilohertz. Quantization is the process of converting a sampled level to a binary code. The number of bits determine the quantization accuracy. The simultaneous or the flash method is the fastest. The sigma delta method produces a single bit data stream. So that is it for today. See you in the next lecture with more on digital circuits. Thank you very much.